So the Calc 3 versions of Calc 1 topics continue. Max-min problems. Remember when you did problems in Calc 1 where you had a function and you wanted to find its absolute max, and maybe it didn't have an absolute min if it went down forever, and you found critical points, you set them equal to 0, etc., etc. Well, we have max-min problems in Calc 3 also, except now, instead of maxes and mins of nice squiggly curves, we have maxes and mins of three-dimensional surfaces. Just like before, we have local maxes and absolute maxes. Sometimes we call these relative extrema and absolute extrema. So relative extrema is the same thing as a local extrema, and an absolute max and min is the same as sometimes you'll see them called global extrema. So a global max and a global min, meaning over the entire domain and range of the function, that's the highest, not y value anymore. Now it's the highest z value. So if you see, we've got a local max over here because there's a little hill, and we got a local min because there's a little valley, and another local min. But that local min is also the absolute min. So every absolute max and min is also a local. This one's a local max, that one's a local max, but now look at the z values. This max has a higher z value than the max down here, so that is the absolute max. So now we're looking for absolute and relative extrema on three-dimensional surfaces. Again, you can look at the PowerPoint for all the pretty pictures and the information about where we're getting these things from. Formal definitions are in there as well. Critical points. Remember, critical points were the places where the first derivative was equal to 0? Well, it's the same thing here, except now I need both the partial derivative with respect to x and the partial derivative with respect to y to be 0. So find the critical points for that function. Let's first find the first derivative with respect to x. That will give me 2x minus 6. And then the partial with respect to y will give me 2y plus 8. I want to find out where these values are equal to 0. So in the first line, that happens when 2x is equal to 6, or when x is equal to 3. In the second line, that happens when 2y is equal to negative 8, or y is equal to negative 4. So the critical point is 3, negative 4. That's the place where it happens. It's an x and a y coordinate. So usually you would say that the critical point happens at x equals 2 or something. Now the critical point happens at x equals 3, y equals negative 4, and then we would throw it back in to find the z value. Just because the first derivative equals 0 does not guarantee a max or a min. So it's not a guarantee that that is a max or a min, but it's just a place where it could happen. All right, how about the second one? The second one has a similar idea, except there's a little glitch to it. So let's find the partial derivative of f with respect to x. All right, we'll get a 2x. Here, x is the variable, y is the constant, so we'll get a plus y. And then the third piece here gives us a minus 2. Right? So the partial with respect to x has a y in it. Well, isn't that interesting? The partial with respect to y is just going to be x minus 1. Okay. Now take the partial with respect to x and y and set them equal to 0, except I can't solve that first line because I got two variables in one equation. What to do? Go to the second line and solve that thing for x. Solve that thing for x, and I get x equals 1. Now, substitute it. So I'll get 2 times 1 plus y minus 2 is equal to 0. And after all that work, y is 0. So here, the critical point is at x equals 1, y equals 0. So every once in a while, you may come across that where you have to solve for one in order to go and find the other. All right, now that we're in 3 dimensions, we have a new question, and that is, how do second derivatives work, and why are they different in 2 dimensions or in 3 dimensions than they are in 2 dimensions? Here's why. In 3 dimensions, you have what they call saddle points, and it looks like the saddle on a horse. That's why they call it a saddle point. But you notice from this point here in the middle, that 0, 0, f of 0, 0, whatever that z value happens to be, depending which way you walk, if you go here, you're going to go downhill. But in the other direction, you're going to go uphill. So you can walk downhill in some directions, uphill in the other direction. At the saddle point, it has a place where the slope is 0. So that's what we call a saddle point. Now, when you go to take second derivatives I put this in here because you'll see this in the PowerPoint. A student sent this to me last year when we were working on these saddle points. And so here is your little laugh for the day. What others see and what I see. You can pause this to appreciate the beauty. I'm going to move on. All right, so the second derivative test. So this is where the dimensions start to look different. In 2 dimensions, there was only one second derivative test. Now, which second derivative do you use for the second derivative test? The answer is all of them. There's 4 of them, right? There's a partial derivative with respect to x and then x again. There's a partial with respect to x and then respect to y. There's a partial with respect to y and then x. And there's a partial with respect to y and then y again. So there's 4 partial derivatives. Now, I put the assumption down the bottom. You're assuming all the partial derivatives are continuous and that you've already found a point to be a critical point, a place where the partials equal 0. What that means is you're going to have to evaluate this at each critical point. Okay, once you evaluate the partials at one critical point, I'll show you what to do with them, then do the next one, then do the next one. In order to organize these better, we're going to set up what we call the Hessian Matrix. And I think the story of the Hessian Matrix is actually one of your questions to answer this week, discussion questions. So to use the Hessian Matrix, here's what you do. You set up all the partials. Partial with respect to x twice, x and then y and then x, y and then y. And then you take the determinant. Now remember the determinant was that AD minus BC thing. So we had encountered this last chapter, 2 chapters ago. They're all blending together. When we had done cross products, and I had said if you take AD down this way and then subtract the product down the other side, other diagonal of the matrix, you'll end up with what we call the determinant. And here we can do the same thing. We can find the determinant by taking the 2 partials with the same variable and then subtracting the other ones. Now you realize that the partial with respect to x and then y and then x are the same thing. That's why the formula down here has the partial with respect to x and then y squared, because it's the same term twice. Sometimes these terms will be constant terms. Sometimes these terms will be functions. Now, if they're functions, then you have to go back in and evaluate at whatever that critical point is that you got. What do you do with it once you have it? So you're going to come up with this determinant, and this is the second derivative test lifted directly from the textbook. My determinant is what I found with that Hessian matrix. If the determinant is positive and the item in the top left corner, the partial with respect to x twice, is negative, then you've got a local max. If the determinant is positive and the partial with respect to x twice is positive, then you've got a local min. If it's negative, then you got a saddle point, and if it's 0, then it's inconclusive. And there is an analogy to this with Calc 1 type things. You had a second derivative test that talked about the second derivative being positive and negative. The same thing happens here. So how do we do this? Let's run through an example, or 2 examples, or 3 examples. Here's my function. X to the 4th, y to the 4th. I got a minus 4x and a minus 32y plus 10. My goal is to find extrema. There could be relative extrema. There could be absolute extrema. There could be multiple extrema. There could be no extrema. First thing is, let's find the partial. So I'm going to slide way up here, and I'm going to write my original function back here at the top. So f of xy is equal to x to the 4th plus y to the 4th minus 4x minus 32y plus 10. So the partial with respect to x is going to be 4x to the 3rd. The second term yields nothing. The third term will give me a minus 4, and that's all there is. The partial with respect to y will give me a 4y to the 3rd minus 32. All right, set each of these guys equal to 0. Over here, when you pull out a 4, you end up with x to the third minus 1 equals 0. If x to the third is equal to 1, then x is equal to 1. That's your only value on that side. Over here, divide everything through by 4, and I get y to the third minus 8 is equal to 0. Move the 8 over to the other side. What number cubed gives you 8? It's got to be 2. So my critical point happens at 1, 2. Okay, from there, I need the second partials. So the second partial, if I take the derivative of x again, then I'll get a 12x. If I take that partial that I have up there and derive it with respect to y, it just becomes a 0. Because if I'm treating x as a constant, clearly 4 is a constant, those two things both give me 0. Right, the partial derivative of y with respect to x is again 0, because if you look at the y and the 32, derive that with respect to x, they're both constants. And the derivative of y with respect to y again is 12y squared. So those are my 4 partial second derivatives. Now, I need to evaluate them at 1, 2. That critical point right there. And I'm going to put those 4 numbers into my Hessian matrix. So 12 times 1 is 12. Clearly the zeros are the numbers that belong over there. And then 12 times 2 squared, well, 12 times 2 squared is 4. 12 times 4, 48. That's my Hessian matrix. Take the determinant of that matrix. So the determinant of my Hessian matrix is going to be 12 times 48 minus 0, which, if I throw it on a calculator, 12 times 48 equals 576. Okay. I'm ready to make a conclusion. The determinant is greater than 0. Go to the top left, that second partial derivative with respect to x is greater than 0. So the two positive partials, if you go back to that list, it should tell you there's a local min. Local min at 1, 2, and then we can fill in the third value by going back to the original function and finding f of 1, 2. I will leave that to you rather than just sitting here while I punch numbers into a calculator, but that's what you do. If you want the actual min, it's going to be 1, 2, and then whatever that thing is up there. All right, let's try another one. Let's try... Oh, this is the graph, by the way. I graphed this clearly on Mathematica. I did not graph it by hand. So this is your set of x values. That's your set of y values. And you notice, and here's your z's. So you notice that it happens when x is equal to 1 and y is equal to 2. Right there in the middle, that's where the minimum is of that surface. All right, so it does work out. All right, let's take a look at another case. In this case, I'm looking for, again, critical points in extrema for this function that's listed here. So let's take some partial derivatives and find some critical points. So the partial derivative of f with respect to x is going to give me 2x plus y squared minus 2. Right, the partial with respect to y will give me 2xy. Now, if I take the partials and set them equal to 0, let's take a look at that partial derivative with respect to y first. Over here, x equals 0 will make that sentence true. So will y equals 0. So let's take each of those and throw them back into this partial derivative up on the top. So when I do that, I get the partial with respect to x equals 2 times 0 plus y squared minus 2 equals 0. And then if I do it for the other variable, I get the partial with respect to x equals 2x plus 0 minus 2 equals 0. So those are the two sentences I get. One with x equals 0, one with y equals 0. The top line is going to give me y squared minus 2 equals 0. The bottom line will give me 2x minus 2 equals 0. All right, what does that mean? On the top, if x is equal to 0, right, so this is the line for x is equal to 0. This is a line for y equals 0. Can you see that over here, if I move the 2 to both sides, I'm going to get a solution of y equals plus minus the square root of 2. Right, because move the 2 over, take the square root, I actually get two values. So when x is equal to 0, I get positive square root of 2. When x is equal to 0, I get negative square root of 2. Now down the bottom is what happens when y is equal to 0. What happens when y is equal to 0? I get 2x equals 2, or x equals 1. So I actually have locations for 3 critical points, which means I'm going to need more than one Hessian matrix. Next thing I'll do then is I'll take a couple of derivatives. So the partial with respect to x, derived again with respect to x, is just going to be 2. Right? The y squared and the minus 2 will go away. The partial with respect to x and then with respect to y is going to give me a 2y. The partial with respect to y and then y again is going to give me a 2x. All right, so if I want a generic Hessian matrix for this problem, I'll get a 2, I'll get a 2y on the top and bottom corners, and I'll get a 2x over there. Now I need to throw in some values. Let's try this first for 1, 0. So our Hessian matrix that we had was 2, 2x, and then 2y and 2y. So the first thing is, let's evaluate this when x is equal to 1 and y is equal to 0. When x is equal to 1, y is equal to 0, I get 2, 0, 0, 2. Right, calculate the determinant. The determinant is 4, right? 2 times 2 is 4, minus 0 is 0. Now, let's calculate it for 0 square root of 2. So I get 2, 2 times the square root of 2, 2 times the square root of 2, 0. Right, calculate this determinant. 2 times 0 is 0, minus 2 times 2 is 4, and root 2 times root 2 is 2. My determinant is negative 8. Now, do you realize that if I change this, if I were to come here and say, let's do it for 0 negative square root of 2, the only thing that would change is those two things would both be negative. But now when you multiply two negatives, you get back a positive. So it turns out that 0 square root of 2 and 0 negative square root of 2 actually yield the same determinant. Let's apply the test. So in the first case, the determinant is 4. The second partial with respect to x is positive, so I get it is equal to 2 is greater than 0. So I get a greater than 0 for both of them. So if the determinant is greater than 0, the second partial is greater than 0, then I've got a local min. So here at 1, 0 produces a local min. So x equals 1, y equals 0, z equals whatever happens when I throw it in. Over here, the determinant is negative, but the second partial with respect to x is positive. Well, if the determinant is less than 0, what that means is I have a saddle point. So I have one of these places where it can go up or down in either direction depending on which way I walk away from it. So the local min in step 1, I can figure out by throwing back into the original equation. So let's see if I can do this fast. X equals 1. And the second piece will just be 0 because 1 times 0 squared is 0. Minus 2 times 1 plus 1. Oh, isn't that boring? 1, 0, 0 is where that local min turns out to be. And the other part is a saddle point. If you want to see what the graph looks like, here's where the graph looks like. 1, 0, 0. That point is all the way down the bottom there. 1, 0, 0. Sitting right on the XY plane. All right, let's take a look at one more type of problem. Let's look at the extreme of for this. F of xy equals 2x to the fourth plus y to the fourth. All right, so take the partial with respect to x, and I get 8x. Take the partial with respect to y, and I get, 8x to the third. Over here, I get 4y to the third. All right, set these equal to 0 to find my critical points, and I come up with x equals 0 and y equals 0. Okay, those are both my critical points. Now take your second derivatives. Second partial with respect to x, 24x squared. Derive that with respect to y, and I'll just get 0, right? 8x to the third derived with respect to y, I get 0. Partial y twice gives me 12y squared. Now, evaluate that at critical point. I evaluate it when x equals 0 and y equals 0, and I get a whole bunch of zeros. The second partial with respect to x is 24 times 0, which is 0. The second partial xy was already 0, then the yx is also 0, and the double y, 12 times 0, is 0. I got myself a zero matrix. So the determinant of a zero matrix is 0. If you go back to that list, it'll tell you that that means it's inconclusive. But does that mean that there's no max and no min? No. If you go back to this original function here, the 2x to the fourth plus y to the fourth, you notice that thing will never be negative. And in fact, when x is equal to 0 and y is equal to 0, then z is also 0. Any value you put in that's bigger than 0 for x or y is going to make it bigger. So it turns out that this thing here is a minimum. So why did the test come out inconclusive? What happens to that 2x to the fourth plus y to the fourth that makes it inconclusive? Here's what happens. You come up with an object that looks like a garbage can, right? A surface with a flat bottom. So the test is trying to figure out what is that one single point that's the lowest point on this object, and the answer is there isn't one single point that's the lowest point on the whole object. There's a lot of points that are the lowest point on that object, and that's why the test comes out inconclusive. So there is a minimum. That minimum is z equals 0. It's just that it happens at multiple points, and so the test can't pinpoint one specific point. All right, from here, in the next video, we'll take a look at optimization problems and absolute maxes.